Any questions from last time? Yes?
So I still have some confusions about how we're defining convergence of curves, of sequences of curves. So in particular, it seems that we have to choose a particular parameterization for each curve, and then we define convergence pointwise.
Yes.
But that seems to depend on how we parameterize the curve.
I know, but we had to distinguish one. We parameterized them by arc length in some metric. So it actually doesn't matter what metric you use, okay, if you think about it. But, okay, I think what you really should think about it is what we're trying to do with discussing convergence of curves. Why did we care about convergence of curves? What we really wanted to know is that in a globally hyperbolic space-time between two points that are time-like separated, there's a path of maximal proper time. So the notion of convergence we used was adapted to prove that. If you keep that in mind, I think it will be clearer what were the choices we made. Although the fact that you make the question shows that I'm not completely correct. Because you probably do have that in mind. Sorry. Okay. I'm not sure what to tell you. Okay.
I have a question.
Yes.
Are there any subtleties with the notion of compactness in infinite dimensional spaces?
Of course.
So, what makes...
Mainly, there are different topologies in infinite dimensional spaces. Sure. And compactness depends on a notion of topology.
Sure.
But our convergence was pointwise convergence. And we always were parameterizing our curves by arc length. So we had preferred parameterizations. And by convergence, we just meant pointwise convergence. We made two arguments that involved convergence of curves. One was for sequences of curves in Minkowski space. We parameterized them in an obvious, not completely natural, but obvious Euclidean metric on Minkowski space. Then there was a more fancy argument that went into proving that spaces of curves, of causal curves in a globally hyperbolic spacetime are compact. And we really needed that for the singularity theorems that we're coming to. It was the same thing. We picked a complete Euclidean metric, and we parameterized our curves by arc length in the complete Euclidean metric. So there are other notions you could study, but we studied a rather naive notion of convergence.
And this is sufficient for...
It was sufficient. It was the right thing for our applications.
I see.
The questions, though, make me worry that that isn't as obvious as I hoped it would be. Any other questions?
If we were looking to fill out some of the details, at least in the topology of that statement, would it be in Wald's book? And if so, where would we look in Wald's book?
Well, it'll be fairly obvious what chapters you want. It might be chapter 8.
8, yeah.
Chapters 8 through 11, 3 of the 4 chapters from 8 through 11
Yeah.
cover the material I'm explaining.
Yeah.
And this will be near the beginning.
There's also some details in the appendix, which is there's
Wald's appendix?
Yeah.
Okay, well, I think if you look, it'll be clear what you want. I, however, have been trying to present this material without excess mathematical detail, which is also what I tried to do in my lecture notes. That was really the purpose of writing lecture notes. Okay, so today we're going to be talking about time-like geodesics, which we just started to discuss near the end on Thursday. So remember, a time-like geodesic may maximize proper time between points. In a physically sensible situation, a small portion, if you take a small portion of a time-like geodesic, it will maximize the proper time between points. But if you continue for a longer period, a geodesic will eventually, the reason that is the case is that the problem can be embedded in a portion of space-time that looks a lot like Minkowski space. And you know that the statement is true in Minkowski space. In Minkowski space, between any time-like separated points, there's a unique time-like geodesic, and it maximizes the elapsed proper time. So the same is true. Technically, the proof requires strong causality. The same is true for a sufficiently small part of a time-like geodesic in any spacetime. The purpose of strong causality is to make sure that the discussion can be carried out in a small region. However, if you continue a time-like geodesic, almost always it stops maximizing proper time. I'll call the proper time tau. I gave the example of the Earth moving around the Sun. The orbit of the Earth around the Sun over 1,000,000 years does not maximize the proper time. You could blast a rocket from the Earth almost at the escape velocity from the solar system. It goes very far away, spends most of the 1,000,000 years at a tremendous distance, then falls back. You pick the orbit so it falls back and precisely lands on Earth. So you have two geodesics connecting the same points on the Earth's world line. One is the world line of the Earth, a geodesic. The other is the geodesic of the rocket ship. The rocket ship was less affected both by the gravitational redshift and by the special relativistic time dilation. So the proper time is greater for the observer on the rocket ship. So the Earth's orbit is a typical example of a time-like geodesic that over a sufficiently long period doesn't maximize the proper time. Now then, we started to talk, actually I can't remember how much I said, but we started to talk about a necessary condition to maximize the proper time. I might be repeating part of what I said Thursday. I can't remember how much of this I said. So there's a necessary condition for a geodesic to maximize the proper time. The necessary condition is that there should be no focal point, also called by many authors the conjugate point. And the picture illustrating this is exactly the same as it was in Euclidean signature. That's really why I started in Euclidean signature. Here's a time-like geodesic from P to Q, but there's a focal point. If some other time-like geodesic starting at Q would have intersected this one before getting to P. So we have a geodesic gamma, a time-like geodesic, but we can replace a small portion of gamma with some other gamma prime. Now, in that situation, remember in that situation, in Euclidean signature, we said that gamma did not minimize the length. In Lorentz signature, though, for time-like geodesics, in this situation, gamma does not maximize the proper time. The proof is the same, but using this twin paradox instead of the triangle inequality. So we just zoom in on a little portion near P prime, which we can think of as happening in Minkowski space. So, okay, the first step is that the fact that you can deform gamma to gamma prime as a path from Q to P prime means that the proper time here is the same as the proper time here, because proper time is constant in a family of time-like geodesics, since time-like geodesics extremize the proper time. So we could replace the time-like geodesic from Q to P with a non-geodesic, which goes along gamma prime from Q to P prime, and then continues on gamma up to P. That's a non-geodesic, but it had a proper time as big as the geodesic that we started with. Now we zoom in on a little portion near P prime. near P prime, we just have, well, we can model it in Minkowski space, and we just have time-like geodesics meeting at the point P prime in Minkowski space. And now, you see, I could replace this little portion of the path with this one. So in Euclidean signature, the triangle inequality says that replacing two legs of a triangle by one shortens the length. But in Lorentz signature, assuming all the paths are time-like, the twin paradox says that replacing the two legs of the triangle by the third one increases the proper time. In a suitable Lorentz frame, this was the path of the twin who stayed at home. This was the path of the twin who made a journey. And as you all know, the twin who made the journey comes back younger. So we increase, in Euclidean signature we reduce length, but in Lorentz signature we increase the proper time by rounding out the bend. So once we pass a focal point, we're never going to be maximizing the proper time. Any questions on that? So this is only a necessary condition to maximize the proper time. It might happen that some totally unrelated geodesic that's not close to this one arrives sooner than P. When we discuss focal points, we're only testing for whether we could make a small variation of our curve that would increase the proper time. But it's always possible, analogous to a first-order phase transition, that there's some big jump that would increase the proper time. However, going back to the case of a focal point, there are some more statements from the Euclidean signature case that have analogs here. So, one is that we don't need all gamma primes to focus at P prime. In other words, we don't need to know that all time-like geodesics from Q would have focused at this point P prime. It's sufficient that there's one way to displace gamma that leads to this focusing. And secondly, and very important, that focusing to first order is enough. The reason is the same as it was in the Euclidean signature discussion. Even if gamma prime, so focusing to first order means that gamma prime obeys the linearization of the geodesic equation. Right? You have a geodesic equation that was satisfied by gamma, and then we linearize it, and we get the equation for a first order deformation of a geodesic. We only need to know that gamma prime obeys the linearization of the geodesic equation, so that to first order, the deformation from gamma to gamma prime doesn't change the proper time. The reasoning is the same as it was in Euclidean signature. So even if gamma prime doesn't obey the geodesic equation at all, just because gamma is a geodesic, when we make a deformation by an amount epsilon, delta tau is of order epsilon squared. So that's delta tau because of replacing gamma by gamma prime. But if gamma prime obeys the linearized equation, then the proper time increase, the proper time change, which will be a reduction, the proper time change, which should have either sign actually, will be of order epsilon cubed. It can have either sign because once you obey the first order equation, well, anyway, in order epsilon cubed, there's no general sign. But what we gained when we made use of the twin paradox near P prime was of order epsilon squared. So therefore, once we have first order focusing, we'll win by this process in order epsilon squared. So all that is exactly the same as it was in Euclidean signature, with reducing length replaced by increasing proper time. and with triangle inequality replaced by twin paradox. So if it sounds like I've been repeating myself, then that means you have listened carefully to the 2 lectures. Now, it's very easy to get focal points because almost any time-like geodesic continued long enough will pass through focal points. And to prove the Hawking's theorem about the Big Bang, we need a criterion to predict the existence of focal points. Well, maybe just by pictures I'll explain that it's easy to get focal points. Suppose we're in Minkowski. Sorry, I'll delay that slightly. Okay, sorry. We're going to start explaining Raychaudhuri's criterion, Raychaudhuri's equation, which is a criterion to predict the existence of focal points. It was the first result that headed toward the modern singularity theorems in general relativity. So, we consider a space-time M and a space-like hypersurface S S could be a Cauchy hypersurface in a globally hyperbolic spacetime, but our conditions are more local, so we don't really need to know that. So here's S. It's embedded inside M. And at each point in S, there exists a time-like geodesic. So through each point, there's a unique time-like geodesic that's orthogonal to S. So you start at a point in S, and you go in a direction in space-time that's orthogonal to S that determines a unique, if you want it to be future-going, a unique future-going time-like direction. And you just go along the time-like geodesic that goes in that direction. So we build, near S at least, a family of orthogonal geodesics. Then we're going to coordinatize M as follows. One parameter is just going to be the time elapsed. I'll call it T. T is the proper time elapsed. And then the other parameter is, of course, going to be the point where the geodesic originates on S. Now, we don't need to really pick coordinates, but I like to be explicit. So I'm going to... So we have a space-time M in it. We have a space-like hypersurface S. Then we pick... Our considerations are local. S might be a global Cauchy hypersurface, but we're going to work locally on S anyway. We pick local coordinates X on S. There are D of them, of course. D is the space dimension, one less than the space-time dimension. For each value of X, we then pick the orthogonal geodesic to S at that point in S. And then it's some curve like that. It's an orthogonal geodesic. So now we parameterize M near S. As we'll see, this parameterization breaks down in general if we're too far from S. But at least near S, we parameterize M by the starting point, a point in S, and also by the elapsed time along the orthogonal null geodesic. So this is a local coordinate system on M, and you can ask what the metric of M looks like in this coordinate system. And the answer is it looks as follows. ds squared is minus dt squared plus a spatial metric, which, however, is t-dependent. And importantly, it's 0 times dt dxi. So there are two claims I'm making. One is that the coefficient of dt squared is -1. The other is that the coefficient of dt dx is 0. So I could have said, you see, we could have said, pick the gauge, G00 equals -1, G0I equals 0. But the trouble with saying it that way is that, as you're going to see, this gauge condition can be imposed locally, but only locally. And how the gauge condition breaks down is going to be important. And to understand that, it's going to be useful to use this language of the orthogonal geodesics, rather than just saying, pick this gauge, as you might be tempted to do as a physicist. So, okay, why is it true that G00 is -1 and G0I is 0? Well, for G00 being -1, that's just because we pick time to be t to be the elapsed time along a geodesic. And that tells you pretty much by definition that G00 is -1. It's slightly less obvious that G0I is 0. To prove that, you see, the curves xi equals 0 are geodesics in this coordinate system. That's how the coordinate system was defined. So that tells us that 0 is d2 xi d tau squared. But the proper time is just t. So this is the same as d2 xi dt squared, which is 0, plus gamma I, well, in general, gamma I mu nu, dx mu d tau, dx nu d tau. But in this case, the only coordinate that depends on tau is t, and dt d tau is 1. So that's just gamma I 0, 0. And that comes out to be a half gij times, I think you'll find it's d0 g0j. So the fact that the curves at fixed x are geodesics tells us that dt of g0I is 0. But g0I at time 0 was 0 because the geodesics were orthogonal. In other words, the condition that the geodesics we considered are orthogonal to S at time 0 precisely means that g0I is 0 at time 0. And then, for the, as I just explained, for the curves that fix x to be geodesics, tells us that g0I remains 0. So our metric is this one. Now, it's going to be very important to know how this coordinate system can break down. So, in other words, can we assume here that t runs from -infinity to +infinity, for example? Well, one obvious reason that we might not be able to solve the geodesic equation for all times is that the space-time itself might end, which informally means there's a singularity where it ended. So, the coordinate system could break down at a singularity. In other words, if the space-time ends. What we're going to be trying to do in a little while is to prove that the space-time has to end. So we shouldn't dismiss this possibility. But in order to prove that the space-time ends, it turns out that it's important to know how the singularity, how the coordinate system can break down without the space-time ending. So how, assuming the space-time doesn't end, how can the coordinate system break down? Well, so if M itself is good, in other words, if M continues as a smooth manifold, what can go wrong with the coordinate system of the orthogonal geodesics? Well, Gij of x and t is always well-defined and smooth. Well, if M is smooth and Gij of x and t is smooth, if M is real analytic, then Gij of x and t is real analytic. Gij of x and t you find by solving the ordinary differential equation for the orthogonal geodesics. And generalities of ordinary differential equations will tell you that roughly the solution behaves as well as the problem does. So to the extent that there's a good spacetime, there's a good Gij of x and t. We might not have a good spacetime, it might end. Then Gij of x and t will misbehave when the spacetime itself ends, or it might misbehave. But as long as there's a good spacetime, Gij of x and t is well behaved. Oh, when I say it's well behaved, I mean simply it's a smooth tensor-valued function on spacetime. So what can go wrong?
There could be a focal point?
Yes, there could be a focal point. But we need a slightly, there's another step we need in the answer. We need to know what Gij of x and t does when there's a focal point. We'll get to that in a second, but there was another hand up, I think? No? Well, what can go wrong is that determinant of Gij could go to 0. In order for this to be a good metric on space-time, or it's not quite enough that the matrix elements of Gij are smooth. We want Gij to be an invertible, well, a positive definite matrix at each point in space-time. But the way it will stop being positive definite, remembering that matrix elements can't go to infinity by general facts about ordinary differential equations, if the way that Gij stops being invertible is that its determinant goes to 0. So the only thing that can go wrong in the coordinate system, unless the space-time itself becomes bad, is that the determinant of G could vanish. Now the determinant of G vanishing corresponds precisely to a focal point. Because what Gij measures is the distance after time t of orthogonal geodesics that had a unit separation at time 0. So, well, for example, if Gij is a diagonal matrix, so there are 3 preferred directions, the eigenvalues are just how relative distances have been rescaled between nearby geodesics. And when a eigenvalue of Gij goes to 0, that precisely means that there are neighboring geodesics that are infinitesimally focused to a point. So the picture would look something like this. The geodesics start being orthogonal, but either the initial value surface or the space-time is curved, and some of the orthogonal geodesics will meet. Well, I'm not sure how many of them I should draw meeting, but when some neighboring orthogonal geodesics meet, determinant of G goes to 0, and the coordinate system breaks down, and those geodesics have reached focal points. Any question on that? Now, it's important to stress once again that having a focal point per se has nothing to do with the space-time being bad. Let's just take the example of Minkowski space. And first, let's consider, let S be a flat hypersurface t equals 0. Well, the orthogonal geodesics will never reach focal points because the orthogonal geodesics would then be just x equals constant. Those are time-like geodesics that are orthogonal to the surface t equals 0 in Minkowski space. They never meet, they never focus, and in that coordinate system, the metric Gij will just be a canonical delta, delta Ij. On the other hand, also in Minkowski space, let's take an initial value surface that isn't curved. Sorry, that isn't flat. Take this S, or maybe this one. Well, I've essentially already drawn it on the other blackboard. You should be able to see that even in a flat space-time, if S itself has some curvature, the geodesics will tend to focus in either the past or the future. depending on which way S bends. So having focal points in the orthogonal geodesics has nothing to do with space-time having a singularity. Or it doesn't have to have anything to do with space-time having a singularity. It could just, it's not completely different. If you're on a swimming pool, you'll see very bright, usually you'll see in a swimming pool, if the sun is out, you'll see very bright ripples on the bottom. All that's happening is that the surface of the water isn't flat, so the light gets refracted. In that case, we're dealing with null geodesics, the light rays, and some of them get focused. So that's a phenomenon that's analogous to this. And it certainly has nothing to do with any singularity in space-time. However, it's just a hop and a skip from understanding how, well, okay, we need Ricciardori's equation, and then we're going to learn, then we're going to be able to learn something about singularities. So Ricciardori's equation is just Einstein's equations. It's just the time-time component of Einstein's equation. So Einstein's equation says that R mu nu is 8 pi g times T mu nu minus a half G mu nu T alpha alpha. I'm going to call this thing here that appears on the right-hand side of Einstein's equations T hat mu nu. So Ricciardori equation is just the Einstein equation. RTT equals 8 pi g times T hat tt in the coordinate system of the null geodesics. So to make this explicit, we need to calculate RTT. So when we calculate RTT, there's a matrix that comes in. I could call it M. M is space-time. Q maybe. Q is G inverse G dot. And so, okay. Well, we're going to be very interested in the square root of the determinant of G, which I'll call V. We're interested in it because, as I explained, the condition for a focal point is precisely for V to have a 0. And then we'll let theta be V dot over V. By dot, I just mean time derivative. So you can see that theta is the same as 1/2 of Gij times Gij dot, which you can also think of as 1/2 times the trace of this matrix Q. And it's traditional to also define the traceless part of Q. I think it's called the shear. I keep forgetting what it's called. I think it's called the shear. Well, it's customarily defined with the 1/2, so it's 1/2 so that I is the identity matrix, or maybe I should just write the Kronecker delta. So sigma is 1/2 of Q minus its trace part. So sigma is defined to be traceless. And then RTT can be expressed in terms of these quantities. So one finds that this is a pleasantly short calculation, and an extremely important one. I considered doing it on the blackboard. But then I decided, well, these students really should do that calculation for themselves if they want to learn general relativity. So it is a homework problem. If you look at the homework, you're asked to do this little calculation. Now, if you've ever calculated the Riemann tensor, you'll know that it's usually painful. But this is an exception, I'm happy to tell you. If you actually do this calculation, you'll be pleasantly surprised. If you haven't done it already, you'll be pleasantly surprised at how easy it is. If you decide you actually want to do it, it should not take more than 10 minutes, I don't think. And that allows for some time to make a mistake or two that you have to fix. So, therefore, after careful cogitation about all those points that I just commented on, I decided not to do it on the blackboard and to leave it to you to do for yourselves. But anyway, that's what RTT is here. And we can write it in terms of theta and sigma. So it's minus theta dot, minus theta squared over d, minus trace sigma squared. You see, RTT, I've written it here in terms of the trace of q or q squared. So you can, the trace of q is essentially theta up to the factor of a half, and sigma is just the traceless part of q. So you can therefore go from here to here. So now we can write Einstein's equations. Well, we can write the Ricciardori equation, which is just this component of Einstein's equations. It comes out to be theta dot plus theta over d, theta squared over d equals minus trace of sigma squared minus 8 pi g times t hat tt. So that's the equation that we're going to use to deduce Hawking's theorem about the Big Bang. Now, what's called the strong energy condition would say that T hat Tt is equal to or greater than 0 at each point and each frame, each local Lorentz frame. To Hawking, working in the 60s, this seemed like a natural hypothesis that this was actually a true statement in nature. It's true for, it's true for ordinary matter. It's true for matter dominated by massive particles. Because, where's the definition of T hat? Okay. T hat is T00 minus a trace term. But for ordinary matter, T00 is positive. And the trace term, well, the spatial parts of T are negligible for ordinary matter. And the trace term, because of the 1/2, doesn't do any harm. So this is positive for ordinary matter. It's also positive for electromagnetic fields, because the trace term vanishes for electromagnetism in 4 dimensions. And T00 is positive again. So from Hawking's point of view, it seemed that this was a good hypothesis that in cosmology we can assume that the strong energy condition is valid. Now from a modern point of view, we'd ask questions. So first of all, a negative cosmological constant obeys the strong energy condition, but a positive one does not. In today's universe, looking toward the future, it appears that there's a positive dark energy which is going to be more important. And therefore, looking toward the future, or even currently, because of the dark energy, one would think this isn't a good approximation in today's universe. However, looking into the past, which is what Hawking did in his theorem, the current dark energy is negligible. However, the Higgs potential of the standard model violates the strong energy condition. It's unimportant in today's universe, but it might have been important in the past at some point. And from a modern point of view, we would think that there might have been cosmic inflation in the past, which would violate the strong energy condition. So Hawking's hypothesis of the strong energy condition would not seem as robust today as it seemed when Hawking made the argument I'm about to explain. But still, Hawking's theorem is a valid theorem about what happens as long as physical conditions are at all similar to what they are in today's universe. In other words, looking back to the past where the current dark energy quickly becomes unimportant. The strong energy condition is valid for as long as we actually know the equations of the laws of nature, but looking back into the past. So Hawking thought he was proving there was a Big Bang. We're going to only prove that there's a beginning of the epoch in which the strong energy condition is a good approximation. But let's go ahead with the proof. So first we have to use the Raychaudhuri equation to prove that there are focal points. You're going to see that everything lines up beautifully to make this work. So trace sigma squared is non-negative, and the strong energy condition says that T hat Tt is non-negative. So the left-hand side is negative. This assumes the strong energy condition. So it's equivalent to say that theta dot over theta squared is equal to less than 1 over d. So d by dt of 1 over theta is equal to or bigger than 1 over d. Now let's go back to our setup with the initial value surface and a point P, and suppose theta equals minus w, which I'll assume is less than 0, at P. So in other words, theta of t equals 0 is minus w. So 1 over theta at t equals 0 is minus 1 over w. And so 1 over theta at any t, well, from this equation, it's equal to or greater than t over d minus 1 over w. So inverting that, we find that theta of t is equal to less than 1 over t over d minus w. But it's sort of more convenient. At t equals 0, w was positive. So to write it in terms of things that are positive at t equals 0, I should write it that way. Theta of t is equal to or less than this. And this, the right-hand side, goes to minus infinity at t equals dw. A theta going to minus infinity means that v goes to 0. So we learned that v goes to 0 at a time no bigger than dw. See, theta was v dot over v. So for theta to go to minus infinity, v dot can be either positive or negative. V, of course, is positive. Theta being negative means that v dot is negative. V dot, as long as the space-time itself is well-behaved, v dot is always well-behaved. So the only way for theta to go to minus infinity is for v to go to 0. But v going to 0 means that we have a focal point. So we've discovered a fact that's kind of amazing. All you need is a condition at one point along S. If it happens that theta is negative at that point, you can predict a focal point with no knowledge about anything that's happening except at that point P. All you need to know is that at one point P along S, theta happens to be negative. Then you can predict that the orthogonal geodesic from that point reaches a focal point within a known time, which is just d times the minus the initial value of theta. Any questions? Okay, now we're ready for Hawking's theorem.
I have a question.
Yes?
Was this independent of initial surface, or was there an implicit one? I guess
We picked any surface. There's any surface at any point in the surface, and all you need to know is that theta is negative initially.
I see. Thanks.
Okay. Okay, Hawking's theorem is a theorem about cosmology, so let's just remember a few elementary facts about cosmology. So, in cosmology we have the simple Friedmann, Lemaitre, Robertson, Walker metric. ds squared is minus dt squared plus r squared of t. Well, it could be just dx squared if you have flat surfaces of homogeneity. I'm setting k equals 0. They're also a variant with k equals 1 or minus 1. For brevity, let me just take this version. And then what you learn in, for example, Weinberg's book on general relativity or any place else, is that, first of all, r dot is positive today. So looking into the past, it was negative. And then solving Einstein's equations for this kind of metric, with r dot being initially positive, we discover that to the extent this is a good approximation, there was a Big Bang singularity in the past. So for the perfectly homogeneous and translation invariant FLRW solution, we just solve Einstein's equations and prove there was a Big Bang singularity in the past. We have, in this thing, we've got the Hubble parameter, r dot over r. Which measures how fast the universe is expanding. Now, the universe isn't really homogeneous and isotropic. So, for some purposes, this is a good approximation, but not for other purposes. Hawking asked the following question. Look, of course, the universe is inhomogeneous and lumpy, if you look at it in detail. As you go back into the past, can it be that the inhomogeneities were more important? This wasn't a good approximation. And somehow, some or all of the universe didn't begin at a Big Bang singularity. So Hawking proved a theorem that says that even if we relax the assumption of homogeneity, the universe must have begun at some bounded time in the past. Well, he assumed the strong energy condition, so the modern interpretation would be that the epoch in which the strong energy condition is satisfied must have begun at a bounded time in the past. Now, Hawking's didn't want to assume that the universe is exactly homogeneous and isotropic, but you could pick, let's say, a Cauchy hypersurface on which the temperature of the CMB is everywhere what it is today, measured on Earth, or at least approximately. This doesn't have to be exact. And then, so you could replace this with a more general metric of the kind we've talked about, of which the FLRW metric is a special case. And then, in this more general setting, H, I think is what I called theta. H is theta over D, I think, maybe. It's, what I'm trying to do, I'm trying to, if you specialize to the case that G, the metric G is just R squared times a canonical delta, then you'll learn that V dot over V is a multiple of R dot over R, which is H. So I'm just, I think the formula is that H is theta over D. So in the FLRW cosmology, H is a constant, often called the Hubble constant. But here, since Hawking isn't going to assume that the universe is homogeneous and isotropic, H is not a constant, it's a function on space-time. But Hawking assumes that H is positive everywhere if we measure time toward the future. But more specifically, he assumes we'll assume there's a lower bound, that H is equal to or bigger than W. In other words, we assume the universe is everywhere reasonably close to FLRW, and FLRW, H would be constant, so maybe we want to assume that H is everywhere at least half what it would be in FLRW. Anyway, we put some positive lower bound on H. Now, if we measure t toward the past, we're trying to prove a theorem about the Big Bang, so it's natural to look toward the past. So we'll use a t coordinate that increases toward the past. And that changes the sign of H, so we'd say that H is equal to or less than minus W. So that means, in view of what we've proved, that all orthogonal null geodesics, all orthogonal time-like geodesics from S focus at a bounded time sorry, I think W is replaced by 1 over W somewhere. Sorry. When I went from here, this equation had a 1 over... Okay. Just dimensionally, my formulas have been wrong. Where the mistake came from is that W was replaced by 1 over W when I wrote some equations in terms of 1 over theta. But then I forgot we had done that. I think. Hopefully it's correct now on the blackboard. Okay, so now we have the setup for the proof of Hawking's theorem. That's going to be so quick that maybe first I'll just ask if there are any questions. So Hawking assumed that the universe is globally hyperbolic, which, remember, means simply that there is some Cauchy hypersurface, which we could take to be the one where the CMB has the present temperature, which is supposed to determine the evolution toward the past and the future. And then he assumes strong energy. Now, so here's the initial value surface, and we're looking to the past. So P is a point in its past. And global hyperbolicity means that there's a path of maximal proper time from P to S. Okay. Yeah, okay. We proved that the space of causal paths from P to S was compact, and that led to the fact that a function like the proper time can be maximized. So there's some path that maximizes the proper time from P to S. This is the step where we use global hyperbolicity. There exists a gamma that maximizes proper time for any path from P to S. It's obvious the statement needs global hyperbolicity because if you remove from space-time a point, making it non-globally hyperbolic, if you happen to remove the point that was on the path of maximal proper time, things would go wrong. What was less obvious, and we worked hard in the first 2 lectures, was to prove that if you are in a globally hyperbolic situation, then there is a path that maximizes the proper time. Now, a path that maximizes the proper time must have no focal points in the segment from P to S. Because we know that a time-like geodesic with a focal point doesn't maximize the proper time between its endpoints. But because we're assuming the strong energy condition, we know that, and because we have this lower bound or upper bound on h being negative less than minus w, we know that a focal point develops within a time d over w. That's because h is negative, and Raychaudhuri's equation. So therefore, the geodesic between P and S has a proper time that's equal to or less than d over w. So we've learned that there's no point in space-time that's to a time more than d over w to the past of the initial value surface. Any point in space-time is connected to the initial value surface by a curve that maximizes the proper time, and that maximum is at most d over w. So the space-time did not exist for a time more than d over w before the initial value surface. That's Hawking's statement about the Big Bang. Question? I saw somebody's hand was up. Yes?
Yeah, does your condition about no focal points exclude P being a focal point?
Well, no, if P is a focal point, the path up to P can still maximize the proper time, but continued beyond P it will not. So whatever is the greatest time you might go up to a focal point, and that time we found is at most d over w, that's the maximum anything could have existed to the past of the initial value surface. Yes?
If you take our universe,
Yes.
it's expanding, so
Yes.
h greater than 0 is seemingly
Yes.
reasonable.
Yes.
What does d over w come
Well,
up to?
see, d over w is within a factor of 2. It's the time you get for the if you took the ideal FLRW solution and estimate the age of the universe, you get a certain answer, which is 13 point something billion years. So you get an answer of the same order of magnitude for the upper bound.
Awesome.
It's simply because you see, that's why I worried that I had something dimensionally wrong. 1 over the Hubble constant is the age of the universe up to a factor of order 1. And this calculation gave 1 over the Hubble constant times a constant of order 1 as an upper bound. So it's a reasonable upper bound, but okay. Any other questions? Yes?
So it doesn't matter which surface as you pick, you always get a bound of d over w.
Well, w will be different for different surfaces. So in any space-time which is sufficiently close to FLRW, you expect there's a lot of hypersurfaces where w has a lower bound. But different s's will have different w's. Yes?
Suppose you have the Minkowski space
Yes.
with some matter in the center
Yes.
that collapses to make, let's say, a star, but not something that processes singularity.
Yes.
Wouldn't we have a negative W in this case? Whether, I mean, either to the future or to the past. And so there would be one traditional
Well, a local negative W wouldn't have told us anything. So suppose you have a point P which is a little bit to the past of S. So there's a geodesic that reaches P, and if P is not very far to the S, if P is not very far from S, it will be proper time maximizing. But if you keep going, it'll not be proper time maximizing, so there'll be something better. But something better will always be an orthogonal geodesic, but it might start from far away. So in your example where you make W negative, locally negative, but not everywhere, what will happen is if you go sufficiently far to the past, the optimal geodesic won't be from the region that you were interested in, but from some region outside. That's what the arguments will prove. The arguments prove that there's always a proper time maximizing geodesic, and if you go sufficiently far in the past, it can't come from the region where W is negative, so it will come from someplace else.
I had a similar...
Yeah, just to finish answering one, though, you picked a space-time where there was a local region where you had this bound on W being negative, but far away it wasn't. So then...
The argument involves having that condition be away everywhere.
Yes, right. Because in Hawking's setup, as Juan just said, W is negative everywhere, so there's no place to run. No matter where the geodesic started from, it had the same problem. Nima?
I was going to ask a question even without any matter. I mean, if we had a wiggly hypersurface,
Yes.
then, as you said, we could have we can have W positive or negative. I guess
But we can't, it's very hard to make it...
Wiggly hyperbolic in the Minkowski space.
Well-
It can't ever be everywhere negative. It has to go be positive and negative somewhere, so zero somewhere. Is that the point? That if I wiggle S, that's both positive and negative.
Well, let's try. So, here we're trying to make them all focus. Sorry. No, sorry. No. I think my picture is wrong. Sorry. I didn't plan this, and I'm not sure what's going to happen if I try to answer on the fly. We can try, though. In Minkowski space, I'm taking the hypersurface t squared equals x squared plus r squared, where t is negative. So, the orthogonal geodesics, I think, are getting closer in this direction, aren't they?
They focus very close to zero.
They focus toward our... Oh, sorry, you're right. I'm not drawing them correctly. I'm making a Euclidean picture. Thanks, Juan. These are the orthogonal geodesics. So, right. So, in this example, the bound where H is negative is satisfied if you're forward-looking. And as one straightened me out, the orthogonal geodesics focus toward r equals 0. So what we learn is that, what we'll learn from the argument is that if you're outside this region, you're not connected to that hypersurface by a curve that maximizes the proper time. It must, first of all, if you're up, it's not globally hyperbolic. So the proof that there's a path of maximal proper time from here to the hypersurface is wrong. And it must be that there isn't one, since if we assume there is one, we'd run into the problem. Obviously, you can have a causal curve that never meets that hypersurface. I wish I could tell you immediately if its proper time can be infinite. I hope so. That would be nice. Regardless, the theorem doesn't work because it's not globally hyperbolic, and we're running into that. But and there's not going to be a curve of maximal proper time from here to that hypersurface. But I wonder if the proper time can actually be infinite. I don't know if anyone can help me with that on the fly. We could figure it out by calculus, but I don't really know. Any other?
It would have to be that any globally hyperbolic surface in the Minkowski space has to have places like W.
Yes. Well, okay. To make W everywhere negative, we have to make it bend drastically like this. Okay. We needed W not just to be negative, but to have a positive lower bound for the argument. If W was positive but could be arbitrarily small, the argument wouldn't have worked. And so I think if you make W, if you put a strict lower bound on W, I believe you'll always get a picture like this one. Any other questions?
Yeah, what you drew again, sorry, over there, are these no geodesics? Because they shouldn't have...
They're null geodesics. They don't look like it, but that's because it looks like the blackboard is a Euclidean blackboard, and we're trying to draw Lorentz signature geodesics on a Euclidean blackboard. So, sorry. They're meant to be time-like geodesics, so not null geodesics.
They will have 45 degrees, right?
No, sorry. They're time-like geodesics. So, the straight lines through the origin at less than a pi over 4 angle from the vertical are time-like geodesics. I don't remember if I said light-like at some point, but I meant time-like. What the theorem proves applied to this example is the following. Take this as an initial surface. The whole space-time isn't globally hyperbolic, but the past light cone of the origin is globally hyperbolic. And therefore, the argument would prove correctly that there's no point in this region more than a bounded time to the future of that surface. That's actually correct. The argument doesn't say anything about the rest of Minkowski space. So obviously, the rest of Minkowski space can go on for an unbounded time. It's not globally hyperbolic. Any other questions?
Just the last question. Why should we take away from the theorem that there is a real physical singularity after this time, or that one of our assumptions was wrong? Like, for example, globally hyperbolic.
Well, how you interpret the theorem is up to you to some extent. Most people think that in the context of anything at all similar to FLRW cosmology, global hyperbolicity is a reasonable hypothesis. And see, we proved in a very strong sense that space-time is geodesically incomplete. Namely, we proved that all backwards, past-going, time-like geodesics are incomplete, with a uniform upper bound on how far they can be continued. When we get to Penrose's theorem, we'll have a much more limited geodesic incompleteness. And in the case of Penrose's theorem, it's genuinely unclear whether it really represents a singularity. Here, most people think that since the whole space-time is ending within a bounded time, somehow there is a singularity back there, as in the ideal FLRW solution. However, I don't think that's completely understood. Any other questions? No more questions? So while I was presenting this argument, I actually had a pang of conscience because I realized at the beginning when I was repeating myself, I forgot to repeat something from the previous lecture. So just to put my mind at rest, so we had this set up. We had a time-like geodesic from Q to P, and we said it doesn't maximize the proper time if it passes a focal point. And then the analysis of that was the same as it had been in Euclidean space, except we have to use the twin paradox instead of the triangle inequality. Now, there's another picture we had in Euclidean space where we had a submanifold that I call W, although in Lorentz signature I usually call it S. In Euclidean signature I call it W. And then we want to look at paths from P to the hypersurface. Instead of minimizing the length, we want to maximize the proper time. And see, in Euclidean signature, the shortest geodesic is always the shortest path is always a geodesic that's orthogonal to W. In Lorentz signature, the longest proper time is always for a time-like geodesic that's orthogonal to W or S. The way you prove that is the same as in Euclidean signature. First, for any path to extremize the proper time, it has to obey the geodesic equation. But if the endpoint is free to move, you also need a boundary condition, which by the same calculation, more or less, as that you might have done in high school, possibly, for Euclidean space, tells you that the geodesic has to be orthogonal. If it's not orthogonal, you could have increased the proper time by moving the starting point. And then, also as in Euclidean case, if we pass the focal points, meaning we have a picture like this one where gamma can be slightly displaced, at least to first order, to another orthogonal geodesic, then we don't maximize the proper time anymore. So I used all this in the lecture, but I'm afraid I forgot to say it. In the part of the lecture at the beginning where I was repeating what we did in Euclidean space, I repeated the story for this version of the story, but I forgot to repeat this version of the story. Nobody asked any questions, so maybe it was so obvious I didn't need to repeat it. I don't know. Any questions now? Yes?
So if we're under the assumption that the past, so in that case, it is not not the whole space is, so the global hyperbolicity region of that surface that you picked doesn't cover the full space, right?
Yes. In this example that we discussed in response to Nima's question.
Yes. But so in this situation, and in that case, it suggests that the region that is in the global hyperbolic is going to be something that is a closed, that has some sort of boundary, right?
Well, I think the proof shows that if you pick a hypersurface where W is bounded below 0, it will always give a picture like this one. That's not a good initial value surface. Its domain of dependence is less than the whole space-time.
If the domain of dependence is the full space-time, it doesn't prove that you will always end up in something that is a boundary, so that you end up with a space-time that doesn't.
If the domain of dependence is the full space-time, it must be that W is not bounded above 0 or below 0. We'd reach a contradiction either to the future or to the past if there was a strictly positive or strictly negative lower bound on W. Any other questions? If there aren't more questions, we've run out of things to say about time-like geodesics. So I guess we'll move on to null geodesics, I think.
There was certain, no question.
Yes.
Interesting theoretic.
Yes.
Let's say, I mean, here the assumption is that infinitely far away on this spatial slice everywhere is pretty close to that FR function.
Yes.
But of course, we might imagine way out there somewhere, there are some other bubbles or some crazy other things happening.
Or as in Juan's question, we might imagine we live in an island universe that becomes empty sufficiently far away. And then Hawking's theorem would be fundamentally untrue.
But surely there's some sense in which locally, within our bubble, we
Yes.
can know maybe
Right.
something
Yes.
super far away.
Yes.
We can say something bad is happening.
Yes.
There's a Big Bang singular. Whereas nowhere is this argument saying the bad thing that's happening is the intuitive expectation, some curvature is blowing on something more specific about the bad thing which is happening. And surely it's got to be true that it's a local statement. It doesn't depend.
Well, one would think that if you had a piece of the universe that's much bigger than 1 over h, which was 1 over w in this calculation, that would be good enough. I don't know a precise theorem, but one would think if you have a piece of the universe much bigger than how far you're looking into the past in this discussion, it wouldn't matter whether the universe really goes on to infinity. The simple theorem assumes that the conditions are valid everywhere. But one would think that a sufficiently big island universe would be good enough. What would be good enough for would be to say that past-going geodesics from our region can't go more than this, can't be continued for longer than this theorem says. It, of course, wouldn't say that all past-going geodesics can't be so long continued. I didn't answer Juan that way because I assumed that in his question, there was a region where W was negative, but it wasn't so enormously big as that. But it could have been. Any other questions? Well, if there aren't more questions, we've run out of things to say about time-like geodesics, so it's time to move on to null geodesics. And hopefully this was so much fun that you're all excited to know what you can learn by studying null geodesics. Null geodesics are more fundamental because they probe causality. So what we can learn by studying null geodesics is more and also ultimately more interesting. So our goals in studying null geodesics well, there will be, one goal will be Penrose's theorem. On singularities. It's a more subtle analog of Hawking's theorem that actually came first historically. And then a second goal will be qualitative results on black holes. And what else? Well, there will be some extra credit questions, such as topological censorship. In general, there's much more that you can learn by studying null geodesics than by studying time-like geodesics. Now, for a null geodesic, there's no analog of the length. There's no natural measure of length or time. A Lorentz transformation can rescale a null geodesic. So there's absolutely no natural way to say whether 2 points on a null geodesic are near or far, or how near or how far they are. So for a null geodesic, we can't minimize or maximize anything measured in a natural way along the geodesic. What therefore can we do with null geodesics? Well, we can say that a null geodesic is prompt if it arrives as soon as possible. Actually, okay. We can say this for a null geodesic, but we can also say it for any causal curve. We'll be making remarks that apply to all causal curves, but null geodesics will be a very important case. So when I say it arrives as fast as possible, I mean the following. You start at Q and you arrive at P along a causal path. And gamma is prompt if there does not exist, if for any point P prime that's slightly to the past of P, there does not exist a causal path to P prime. So, in some coordinate system, P prime is at the same point in space as P, but earlier in time. A signal is prompt if it arrives at a given point in space as soon as possible. So, if there is a signal that could have arrived at P prime, then the signal that arrived at P was not prompt. This is my terminology, by the way. It's not standard in the literature. I found that people in the literature were talking slightly in circles because they didn't have a name for this notion, so I just started calling causal paths that arrive as soon as possible prompt. So, well, one statement that's analogous to what we said in both Euclidean signature and also in Lorentz signature is that a sufficiently small portion of any null geodesic is prompt. Well, even farther back, I should say that in Minkowski space, null geodesics are prompt. So in Minkowski space, if 2 points are light-like separated, there's a unique null geodesic between them, and it's always arrives sooner than any other signal could have arrived at the same point. There's never a causal path that would have beaten a null geodesic. When I draw a dotted line, it's a hypothetical curve that doesn't exist, right? So this hypothetical dotted line that gets there, it's a causal path that arrives to the past of P. Doesn't exist if P is null separated from Q in Minkowski space. Now in any spacetime, a sufficiently small portion is similar to Minkowski space. So therefore, a sufficiently small portion of a null geodesic is prompt. But as in all the other cases we've discussed, if you continue a null geodesic for long enough, it stops being prompt. Let me give you an example. We see multiple images of the same supernova explosion sometime when we get lucky. They don't arrive simultaneously. So if we see 5 signals, the 4 that did not arrive first were not prompt, obviously. So that's a real-life example of non-prompt null geodesics. The signals that took the long way around in traveling through some gravitational lens to reach us from the supernova. Now, promptness is a very strong condition, but I'm not sure how much I want to say about it today, because I don't want to rush. Okay. If no one wants to ask a question, just slow me down. I'll have to say something, because we do have a few minutes. But I don't want to say too much, because I want to give a coherent explanation on Thursday. One fact I'll say is that, well, I used this definition before, but let J plus of Q be the causal future of Q. So in Minkowski space, the causal future would be the future light cone and its interior. It consists of all points that can be reached from Q by a future-going causal path, either time-like or null. In Minkowski space, you'll see that a point in the interior of the causal future can be reached on a time-like path. The points that can only be reached on null paths are the boundary points. Every point could be reached by a null path. You could spiral around inefficiently and get somewhere along a curved null path that you could have reached along a more efficient time-like path. But the points that can only be reached by null paths are the ones on the boundary. And some of that is true in any spacetime. In any M, more or less by definition, there's a prompt causal path from Q to P if and only if P is in the boundary of J plus of Q. So, well, you see, if P is in the interior of J plus of Q, that means points in a little neighborhood of P can all be reached from Q are all contained in J plus of Q, so they can be reached from Q by causal paths. That include points a little bit to the past of P. And therefore, if P is in the interior, there's no prompt causal path from Q to P. If P is in the boundary, then by definition, since P is in J plus of Q, there is a causal path from Q to P. But if P prime is slightly to the past of P, it would not be in J plus of Q. So therefore, we find that more or less by definition, P is in the boundary of J plus of Q is the same as saying that there's a prompt causal path from Q to P. I think I'm going to end with this remark, and we'll study prompt causal paths more systematically on Thursday. I'm not certain if we'll get to Penrose's theorem Thursday or the following Tuesday. Maybe not till Tuesday. Okay.